Good morning, ladies and gentlemen. Welcome to the Symposium of newly elected academicians in 2022. Today, it's our great honor to host Dr. Teh Chung Ho as our speaker to share his journey of a research career. First, please welcome our director, David Wu, to address the opening remark as well as the brief introduction for Dr. Ho.
Thank you, Cedric. It's a pleasure to be here, and I just want to express our delight to be able to host the symposium to honor the new academician, Dr. Ho, who was actually elected in 2018, but as we know, the pandemic has gone on a little longer than we all hoped, so we are still happy to have him here today, and part of this is for us to have a chance to get to know Dr. Ho's accomplishments a little bit better. But we hope that one day we can invite him to come here in person and get to know us as well. So, that's something that we hope to do in the future. But let me just preface this by saying that I think this is a particularly meaningful symposium at this time because I think, the awareness is just increasing, the urgency is just increasing for us to look at how the power of chemical transformation can be really significant for society. And what Dr. Ho has done in his career really in some sense exemplifies what that type of basic innovation can do for society. But let me just tell you a little bit about his background so we can understand his trajectory a little bit. So Dr. Ho actually received his bachelor's in chemical engineering from Donghai University and then did a PhD in chemical engineering as well at the University of Delaware with Mort Den. On a topic which is a bit different, he actually worked on the rheology of polymers and really did some seminal work there looking at the flow instabilities that's actually still very much impactful today in that area. But after completing his PhD, he actually went on to work in industry right away. He actually went on to the Halcon R&D Corporation between 1976 and 1980, where he developed a multi-component metal oxide catalyst for selective oxidation of methacrylene to methacrylic acid. After that time, he joined Exxon's corporate research labs in 1980, which is one of the premier industrial laboratories for doing basic research as well as applied research. And he received a Technology Incentive Award for his research and leadership in 1985. So he worked basically about 34 years at Exxon Research, working on hydrocarbon processing and particularly on catalysis. In that period of time, he published 99 papers and had 54 patents, and he's been a consultant for many international energy companies. During that time, I would say, the impact of his work was recognized with a number of awards, but I'll just mention a couple which are on the slide here. He was, before being elected to the Academy here, he was elected to the U.S. National Academy of Engineering, which is also a great honor, 2016. And prior to that, he actually received both the Evans and the Wilhelm Award, which are both a Lifetime Achievement Award and also an award for reaction engineering. And so it's interesting to see, even though his background in his PhD work was in a different area, that he really had this large impact. And I think I just want to say to the younger people in the audience here about how it's important to really think broadly about how your training can really have an impact. And nowadays, especially, the multidisciplinary and interdisciplinary aspects of the problems really require that broad thinking. So in addition to those awards, Dr. Ho has remained active in service, and just recently he's been on the advisory board for the College of Engineering, both at the New Jersey Institute of Technology as well as in Missouri University of Science and Technology. I guess maybe that's probably a good place to just, I don't want to take too much time here, and just let Dr. Ho tell his story. So please join me with a hearty welcome for Dr. Ho to give his lecture.
Okay, it's really my honor. And a tale of two catalysts, which that means that the traditional hydroprocessing catalyst has been used by using supporter catalysts. The supporter is alumina or silica alumina. And the second catalyst, and ExxonMobil has spent a lot of times to develop so-called unsupported catalysts, and we call bulk sulfide catalysts. Okay, so bulk sulfide catalysts meaning that you don't have any supporter, you don't have any metal oxide there. Then, so and what we found that if we develop two catalysts, then you synthesize two different properties, then you can generate some type of synergistic effect there. Okay, so the World Health Organizations in 2016, and they claim that 92% of the world populations they don't breathe in very clean airs. Okay, and also that there's air pollutions causes 8.8 million premature deaths per year, and the European Union cutting greenhouse gas emission by 55% in 2030s. In 2050s, they have to achieve almost zeros. And a lot of pollution stuff that contains SOx and NOx, PM 2.5, and generate acid rains and can cause asthma, okay, and lung cancers, okay, and all kind of problems. Okay. Next. Okay. This shows the global PM 2.5 distributions. You can see that the red area, the Latin America's area, China, is pretty very severe. Okay, and I think Taiwan is much better off here. You can look at the pollutions, not even only in daily life, and also for marines, and also you have a lot of industrial areas. Okay, the majority of these pollutions are generated from some so-called organic sulfur, organic nitrogen heterocyclics. Then these are the molecules contains heteroatoms, atoms sulfur and the nitrogens. And there are two types of nitrogen compounds. One is the the fat membranes, okay, like a copper doors, 6 membranes, okay, and these are two types of nitrogen compounds. Okay, next. So if you want to develop a highly active sulfur HDS catalyst, okay, a lot of countries like European Union, Japan, Korea, Australia, China, Singapore, Brazil, over the years from 1990s to 2020s, saying the sulfur specifications in the transportation fields start with them at 10,000 ppm and all the way over the years, and drop to like 10 ppm, okay, the 2010. So these are the sulfur specs for different countries here. So as you decrease the sulfur content in the oil, go ahead, go back there, go back. Okay, so if you want, so that means if you want have a very high HDS percentages, sulfur, the desulfurizations, then you have to increase your reaction volumes. So the percentage of HDS from 0 to 100%, okay? And if you use some type of catalyst, suppose you use a catalyst and the reaction orders, first orders, okay? Then which means if you want to get a 95% HDS, the volume of the reactors increase exponentially. That's the first order kinetics. And what we found that a lot of very refractory sulfur compounds, okay, if you want to desulfurize them, the reaction order is much higher. Instead of first order, it becomes second order. Then the reaction volume even higher. For example, let's say if you have 80% HDS, you have a second order kinetics, which means some of the sulfur compounds, the kinetics order is higher, then you have higher reaction volumes. Okay, so that's the economics analysis. So you have to decide which are the sulfur nitrogen heterocyclic compounds are the troublemakers. Okay, there are hundreds of all kind of different all kind of heterocyclic sulfur nitrogen compounds. So we are able to identify which are the most important heterocyclic nitrogen compounds. Okay. So at the bottom here, the International Maritime Organizations, the 2020s, they want to lower the sulfur specs from 3.5% to 0.5%. The International Energy Agency for petrochemicals productions. Okay, petrochemicals is also very important. Okay, so their estimation is that by 2020, 2030s, then this chemical productions account for 30% of global oil demands. So this is, we are talking about both oil industries and also petrochemical industries. Okay. Next. So the agenda I'm going to talk about today is that, as you know, the traditional catalyst, supporter catalyst, and the most commonly used supporters is alumina. The second one is silicon alumina. And what we have been working on is so-called unsupported or bulk sulfide catalysts. So for hydrodesulfurization or hydroprocessing catalysts, the catalyst has to have two different type of active sites, and hydrogenalysis and hydrogenations. Hydrogenalysis means bond breakings, the carbon sulfur bond breakings, and the carbon sulfur nitrogen bonds. And hydrogenation is add hydrogen to saturate the change from double bond to single bonds. Okay. So the first step we had to develop correlations. If you want to, you have all kind of petroleum fractions. You got cycle oils, heavy oils, diesels. So for each type of oils, you want to have analyzed the property and the reactivity correlations. For example, they take diesel oils, okay, and you take diesel oils, you can analyze the molecular compositions, okay, by mass spec to find the composition of the hydrocyclic sulfur, hydrocyclic nitrogen compounds. Then once you identify these hydrocyclic sulfur nitrogen compounds, then you have to do some experimental work to find out you correlate the hydrodesulfurization and hydrogenation activity and the relationship between the composition of the compounds, the property and reactivity correlations. And what we found is that the most important problem is you want to have a clean fuse. The organic heterocyclic nitrogen compound are the troublemakers, okay? But also, of course, we want to desulfurize the fuse. So we have to find the hydrodesulfurization and hydrogenation kinetics in the mechanism, okay? Then this type of approach, we have to quantify to gain a predictive understanding of the active sites and the turnover frequencies, how fast the reaction on the catalytic surface, okay? So there are two types of active sites or type of reactions. So the both reaction, hydrogenation and hydrogenalysis, are important. So we have to design a reactor that we have find an optimum trade-off between hydrogenation and hydrogenalysis. And as a result, we develop a catalyst we call stack bed reactors for ultra deep HDS, which means that hydrogenation, hydrogenalysis trade-off. By hydrogenations, I means that we need to use bulk sulfides and supporter catalysts. Supporter catalysts, you use hydrogenalysis, okay? Now, you look at the refinery, you have a lot of feedstocks there, okay? Hydrocarbon feedstocks. You, after the processings, you generate the oil, you generate the ultra clean fuels, and you remove some gases because after hydrodesulfurization and hydrogenation, you generate hydrogen sulfide, H2S, and then ammonia. So what we found that the most relevant model compounds, because the species in the oils is tremendous, right? Then we found that the typical model compound we can use to experiment and to gain some mechanistic understandings. So what we found is for multi-ring heterocyclic sulfur compounds, DBT, dibenzoxyalphine, and is a very good representative heterocyclic sulfur compounds. And this type of sulfur is very easy to treat. But if you have like side chains, here on the right-hand side is a 4,6 diethyl DBT. And can see that the diethyl, you generate a steric hindrance to protect the sulfur. So which means that the sulfur in that molecule is much more difficult to remove. When it comes to heterocyclic nitrogen compounds, we have two types back there. The carbazoles, it's a five-member ring, and the quinoline, 6-member rings. So the quinoline is more basic, and the carbazole, the basicity is lower. So we found that we cannot use the real feed study. We don't want to use real feed study, and then we have to use the model compounds. Use model compounds, you can understand the mechanism, and then you can find a way how to design the reactors. Okay. So there are two types of catalysts. On the right-hand side here, we talk about supporter catalysts. So you do have a supporter. You have alumina or silicon alumina. So you deposit some of the cobalt molybdenum sulfide, nickel molybdenum sulfide on the top of the supporter catalyst. Okay, so the cobalt becomes CO9S8, okay, and moly becomes MOS2. These are the conventional supporter catalysts. So if you look at a catalytic active sites, the majority of the catalysts will be the sulfides, and you have a lot of vacancy there. And then I indicated in the bottom right-hand side bottoms. So the nitrogen heterocyclic compounds will react with the catalyst and produce a product, then remove sulfur and the nitrogen heteroatoms. Next. So one of the most difficult to treat oil is light catalytic oil, light catalytic cycle oils. So LCCO is a very tough oil to treat. So we start off using the commercial catalyst, cobalt, molybdenum sulfide, supported on gamma alumina. Okay. So we take a different type of oil, cycle oil. The cycle oil, some cycle oils have a 20 ppm, 640 ppm, 160 ppm. Okay. Then we found that the HDS rate, the rate constant, okay, is a function of the nitrogen content in the feed. If you have a petroleum fractions contain nitrogen, then the nitrogen is the troublemaker if you want to desulfurize the sulfurs. So there's a direct, pretty strong correlations between the HDS. So if you want to have very low sulfur contents, you need to have to remove a lot of nitrogens. Next. Also, in the refinery, during the hydroprocessing process, as we all know, the hydrogen positive pressure is also very important. Okay, again, and you need a high pressure of hydrogen, so you can dissolve a lot of hydrogen in the oil, because the catalysts also need hydrogen to do the hydrogenation and hydrogenolysis. So hydrogen solubility is increasing function of pressures. The higher the pressure, the higher solubility. Of course, you don't want to run very high pressures, but if you have an active catalyst, so you can lower the pressures. Okay. Next. Okay. So there's a group of people at University of Delaware. Okay, Professor Gates. I was there when I was graduate schools. Okay, so we have done experiments. There's one of the graduate students there. We take model compounds, then we take different sulfur compounds, and 1, 2, 3, 5, 6 as a function of the boiling points. And we found that the relative activity rate, okay, if you have a very simple fat membrane sulfur compound, the reaction rate is very high. And going down, the molecule become larger, the boiling point much higher, the heavier. So you can see you got at the bottom here, you have the 3-ring sulfur compounds. And also I indicated here, it's 4,6-dimethyl DPT. So the reactivity is 6.9. If you have a 6-ring membrane sulfur compound, reactivity is 100 and drop to 6.9. So it looks like that as you increase the boiling point, when the molecule become bigger, and also you have a lot of side chains, then you create a stagger hindrance, then the HDS become much more difficult. Okay, this is the experiment was done at 300 degrees C and 10.5 MPa. This is very insightful data. Okay. Next. Like I mentioned that all hydrotreating catalysts have two functions, hydrogenation, hydrogenalysis. Again, if you use a supporter catalyst, if you start with dibenzoyl, let's assume the reactivity 1.0. This is the standard model compounds. HDS have two reaction pathways. And if you use supporter catalyst, the most important pathway for HDS of DBT is hydrogenalysis, which means you take the sulfur atoms out, you make biphenyl, the upper part, the red part, okay. If you do a if you do for DBT HDS, the hydrogenation rate is very, very slow, very, very slow. So you make a very little cyclohexane. Okay. So which means when you use supporter catalyst, the hydrogenalysis is very high. Hydrogenation is very low. So we develop what we call Hydrogenation Index, HI. If you do a standard model compound experiments with DBT and the DEDBT, and into experiments, you control the temperature like 90 degrees C, then you run the experiments on supporter catalyst, let's say 90% HDS, you can calculate the ratio of CHP over BP. CHP represents hydrogenations. BP is hydrogenalysis. So HI index is indication of hydrogenation selectivity of the catalyst. We call hydrogenation index, HI. Okay. So this is very important. This is very useful index. We have a standard conditions, temperature and pressures, and the 90% percentage of HDS. And once you do a lot of experiments using modern compound, you can prepare different catalysts. It compares the HI of different catalysts. Okay. Now, if you want to remove the 4,6-DDBT, which means they have a staggered hindrance, the reactivity become much smaller. Instead of 1.0, 0.07. You can see that over the supporter catalyst, the reactivity difference is by orders of magnitude. And here, in this case, the hydrogenation index is very, very low, very high. Okay, then which means for the refractory sulfur compounds, okay, you need a high HI catalyst. HI is 6, and because you predominantly product is you have to go through the hydrogenation first, okay, whereas the DBT case, the hydrogenalysis is more important. So the model compound tell us that you have to use different type of catalyst. Okay, and for 4,6-DBT, you need a hydrogenation catalyst. For DBT, you need a hydrogenalysis catalyst. Okay, good. Okay. The mechanism for HDS of DBT and the DEDBT. DEDBT 4,6, the sulfur, the side chain, the ethyl side chains at a beta position. Okay. Now, the DBT and the DEDBT, the absorption is different. When you use the supporter catalyst, then you use DBT, then there's the bonding between the molecular and the catalyst is a sigma bindings. And this MOS2 have a lot of vacancy sites. When the DBT comes in, the absorption is sigma bonding, which means a vertical absorptions is vertical. And when you use the same catalyst, supporter catalyst, if you want to remove sulfur from the so-called sterical hindered HDBT, because the DBT is HI high, HI is very high, hydrogenation. So the absorption is not vertical, it's flat, it's pi bindings, flat. And so you have to have, because of flat, you need a lot of vacancies there. So that tells us that if you want to remove the so-called DBT and also the 4,6-D DEDBT, the easy sulfur and the hot sulfurs. When the hot sulfurs, you need a pi bonding, and easy sulfur need sigma bondings. And the sigma bonding can be offered by supporter catalyst. The pi bondings can be offered by the unsupported catalyst because they have a strong hydrogenations. Okay. Next. So another important information we need to require, we have to find the sulfur, the property and reactivity correlations. So we take the again the LCCO, we run with this on a supporter catalyst. We increase the space time and follow the HDS, and the right hand side is percent HDS, percent sulfur in the product. So when you use the reaction time is very low, you start with high sulfurs. When the reaction time much longer, and we found that the HDS is become HDS but higher. Then we have 3 regions. The first region is so-called deep HDS. And the middle gray region is the transition regions. And the bottom there, yellow is ultra deep HDS. And the sulfur concentration is order of magnitude lower than the sulfur in the upper regions. And we found that the HDS rate, by using our correlations, we found that the HDS rate depends on the API gravity, American Petroleum Index. Okay, gravity. It's basically it's the density of the liquids, and also the amount of DBT concentrations, and also amount of hydronitrogens. So that means the higher API gravity, the HDS rate will be higher. If you have a lot of DBT, the HDS is lower. If you have the nitrogen, it's lower. Okay. Now the 3 regions, HDS, deep HDS, API is the most important. But if you only remove sulfur at very low level and go to the bottoms there, the yellow regions, the so-called ultra deep HDS regimes, and we found that the percent of HDS is directionally proportional to the nitrogen contents. You have constant correlations, A minus Bn. The higher the nitrogen, the lower the HDS in the ultra deep. So we're not interested in the deep HDS levels. We are interested in ultra deep HDS levels here. And what we found in the ultra deep HDS regimes, we look at the using the electroscopic ionizations, GC chromograms. We found out the after the high HDS like 0.01 percentages, we found that the heterocyclic nitrogen compound that survives, our majority is a non-basic. Non-basic means a 5-member ring nitrogen compound. They are carboxyls. They are the other type of nitrogen compound is a 6-member ring nitrogen compound, like quinolene. It's a basic. When we found that in the ultra deep HDS regime, the remaining sulfur compound predominantly are carboxyls, alkyl carboxyls. Okay, we know that carboxyls are the troublemakers. Okay, so what we do is in our laboratories, we synthesize in our laboratories. We make ourselves the 4,6 diethyl carboxyls, and also we use quinolines as some model compounds, and we do model compound studies. Okay. If you want to do real feed studies, it's so complicated, and we have to use a very representative nitrogen compound and sulfur compounds. Next. Okay. So for sulfur compounds, we in our laboratory we synthesize 4,6 diethyl DBT. 4,6 diethyl DBTs is the bottom here. Then we also synthesize the ethyl carboxyl, 3 ethyl carboxyls, and we run the model compound experiments and on a supporter catalyst. So the percent HDS versus the amount of nitrogen as carboxyl. You can see that you have the nitrogen very, very low. Let's say like about like the 5%, 5 ppm nitrogen. Okay, the percent HDS on the on the supporter catalyst, and take a nosedive. HDS very, very, very low. Nitrogen, very small amount. Have very strong effect of nitrogen poisoning. But if you run a DBTs without stable hindrance, and DBT HDS pretty high. Okay, so the effect of nitrogen is very small on the supporter catalyst. But here, the message here is that the sulfur much more vulnerable to nitrogen inhibition. Okay, the sulfur here, the stagger hindered sulfur. Okay, but the DBT itself is not very sensitive. Control the nitrogen. The carboxyl is the troublemakers. Support the catalyst. Next. Then we need to find out the mechanism of the carboxyl kinetics, and we use model compound. You use the 3 ethyl carboxyls, and the reaction pathway is the predominant hydrogenation pathway. Okay, it's the hydrogenation, and so in order to take nitrogen out, you have to go through a sequence of hydrogenation reaction. You need to saturate one aromatic ring, another aromatic ring, and then slowly you break the carbon nitrogen bonds. Okay, very slow. Then you take the nitrogen out. The reaction becomes faster. So there's a pretty slow process here. Okay. So for HDN of carboxyl, you need help from hydrogenations. Okay. This is an experiment done at 1,000 psi. Okay, next, yeah. Like I mentioned before, there are two types of carbozoles, two types of hydrocyclic nitrogen compound. The 5-member rings is carbazole. The 6-member ring is quinolene. So of the two heterocyclic organic nitrogen compound, carbazole is far more refractory than quinolene. So we compare the quinolene HDN versus the carbazole HDA, carbazole HDN model compound experiments. So we do the experiments, percentage of HDN versus the pressures. So you look at the model compound studies, and the experiment we did it with we used a solvent 1-methyl naphthalene, and we added the nitrogen in the feed. Okay, the experiments carried out at 300 degrees C. We had two different model compounds. One is quinolene, the other one the 3E carbozoles. We changed the pressures, so we can see that the quinolene is pretty flat. The 6-member rings is more basic, and so the dominant mechanism is hydrogenalysis. Whereas the 5-member rings, the 3E carbozoles, and the 5-member rings, they need hydrogenation first. So that's why in the beginnings, the hydrogen pressure is very low, then it will be difficult to remove nitrogen from carbazole. You have to increase pressures. And then the carbazole goes through the hydrogenation reactions, then followed by hydrogenalysis reactions. So carbazole requires hydrogenation, selective catalyst, and quinolene doesn't need a hydrogenation selective catalyst. Yeah. So basically, to summarize here is carbazole 5-member ring HDN is limited by hydrogenation. So they require a high HI catalyst. So high HI catalyst meaning the hydrogenation selectivity must be higher. Now, quinolene basically is limited by hydrogenalysis. Then let's compare the bulk catalyst and the supporter catalyst. The previous slide is the bulk as a supporter catalyst. So now we compare the two catalysts, bulk and supporter. A different story here. And both experiments, again, it's a volumetric activity, HDS, versus the hydrogen partial pressure. And here is quite interesting. If we run the experiment with a 79 ppm nitrogen, it's very small amount of nitrogen there. Okay. Then we compare a bulk sulfide catalyst, it's a cobalt-moly. Another catalyst is a blue supporter catalyst. And you can see that the bulk sulfide catalyst have much stronger response to hydrogen pressure, which means that bulk sulfide catalyst is a high HUI catalyst. Their hydrogenation selectivity is higher. They prefer hydrogenation than hydrogenalysis, whereas HDS supporter catalyst prefer hydrogenalysis. Now, if you look at another bulk sulfide, which is the noble metal sulfide, ruthenium sulfides, versus another supporter catalyst. Okay, here, ruthenium sulfide is a noble metal sulfides. It's very expensive, but hydrogenation much higher than the cobalt-moly sulfide. Cobalt-moly sulfide is not a noble metal sulfide. You can see, actually, the HDS activity at low pressure, the bulk sulfide actually lower. So if you can find some noble metal sulfide, you can increase the hydrogenation tremendously. Okay, so this shows you the difference between support and the box sulfide catalyst. Like I mentioned, carbazole is a big troublemaker. HDN reactions, like I mentioned before, limited by hydrogenations to require require a catalyst to have a high hydrogenation selectivity, then a high HI catalyst. So high HI catalyst meaning that we need to have a box sulfide catalyst because we have a higher hydrogenation selectivity. Next. Okay. So here is a typical volcano plot. To remove sulfur and the nitrogen, we had to have some type of compromise because sulfur required hydrogenalysis and box sulfide hydrogenations. And we have three catalysts here. The left-hand side is molybdenum sulfide without promoter cobalt. And the middle one has a cobalt, small amount of cobalt molybdenum sulfide, a tiny amount of cobalt there. Increase the HI tremendously, meaning that box sulfide prefer hydrogenation. And also if you add a cobalt without support, they can increase hydrogenation selectivity. And then the far right-hand side is supporter catalyst. Here we show that hydrogenation, okay, box sulfide prefer hydrogenation, supporter catalyst preferred hydrogenolysis. Okay, next. And because we don't want to use LCCO. LCCO is too complicated, and we use a model compound like I mentioned before. And in order to analyze the kinetics, and we have to do some transient experiments. We use a plug flow reactors, and the plug flow reactor is vertical. Okay. Here we use horizontal to vertical. We have a pilot plan. We design a pilot plan. Okay. And we found we put it into supporter catalyst. You have sulfur in the feed and sulfur in the product. Okay. Then the reaction is the sulfur will absorb on the catalyst surface. Okay. And we have the HDS reaction, reverse. Okay. Then first just hydrogenalysis, make a product. Now, at the beginning, we run the curve here is on the lower part here. We start with 4,6-diazo-DBTs, and we run experiments. Once we reach steady state, 4,6-diazo-DBTs. Okay, run steady state, high HDS. At some point, with steady states, we add 5 ppm nitrogen as a carbazole in the feed. Then we inject this nitrogen in the feed. Then after that, you can see the HDS start to drop because of nitrogen inhibitions. So you can see HDS keep drop. In the meantime, we also measure the sulfur in the product. Okay, in the flow outside. Then we can analyze the products. NP is a nitrogen product, so we have a nitrogen NF sub F is nitrogen in the feed. Then we move nitrogen, some nitrogen. Then we collect the the sulfur survive. So we analyze this. Okay. So the transient experiment is that we start with a steady state, only HDS. When we reach the steady state, at time 0, we add 80 ppm nitrogen, we perturb the systems, and then we collect the data and look at the data at this HDS response. So what we call stimulus response experiments. So to collect data showing on the right-hand side, low part. So percent HDS initially is very high. At time 0, we put 80 ppm nitrogen. We can see nitrogen drop dramatically from like 70% drop to almost like 10%. Whereas the sulfur contents in the product, the effluent liquids, and gradually increase. And this data is very, very important. And we can write a mathematical models. Okay. So this is inhibition dynamics on the catalyst surface. So you have to, if you want to write a mass balance reactions in the transient steady states, and you have to find different time scales. If you have different time scales, well, you can simplify the equations tremendously. So that different time scales, the HDS time scales and absorption time scales are much larger than the HDS reaction, and nitrogen and sulfur and HDNs. And desorption time scale is much longer, which means absorption is very easy. And desorption is taking much longer time. HDS reaction time scales are much smaller. So you kind of write down the partial differential equations, and you can, in so doing, it can simplify the systems very well. And you can calculate the fraction of nitrogen composition as a function of time during the transient state. You can follow the traveling waves there, and you can calculate back out all the rate constant there. So. Next, yeah. Yep. So we can generate the plot, three-dimensional plot, the spatial temporal plot here to see if the fraction of the nitrogen on the left-hand side lower part, the fraction of nitrogen occupation, the z directions, and also time the reactor produces, and also know the sulfur fractions in the feed as function of time, and also the positions of the reactors, and also fraction of sulfur occupied on the surface. You can see this three-dimensional plot, and you can basically we sort of like we can understand what's happening inside the reactors. Yeah. Next. Yeah. So the transient experiments give us information like this. Okay. There are two type sites, hydrogenation sites and hydrogenation sites, and we can quantify this. The hydrogenation site, we found that is more vulnerable to nitrogen inhibitions. Hydrogenation site is more resistant to nitrogen inhibitions. So the model compound is a DBT, 3E carbozoles, and we can calculate the hydrogenation site is per gram of catalyst is 157 micromole nitrogen atoms, and hydrogenation site is 86. Okay. Then we can define a dimensionless parameters we call nitrogen inhibition intensities. And intensity is the G value is the rate constant on the surface times by multiplied by the amount of sulfur in the feed divided by the rate constant for HDN. Then we found that the for hydrogenation site, the nitrogen inhibition intensity is 8.4, whereas hydrogenalysis is 2.2. The reason people use cobalt and the role of cobalt, we found out based on the result, can enhance the tolerance of nitrogen inhibitions. Okay, yeah. And here we say that the hydrogenation site divided by hydrogen, the inhibition intensity is 4. So that means that the hydrogenation is much vulnerable to the nitrogen inhibitions. So this is so far we use model compound. Everything we're trying to understand the mechanism of the kinetics. Okay. Then we come to catalyst aspect. Okay, and all so far we discussed the supporter catalyst. Okay, alumina, gamma alumina, supporter catalyst. Now we'll look at this the book sulfide catalyst here. Again, it's a trimetallic catalyst here. Okay, or bimetallic catalyst here. So you take a precursor, called ethylene diamine molybdenate. Okay. You dissolve this ethylene diamine. Okay. Then you put a cobalt there and you precipitate and make a cobalt moly oxide here. You have a hybrid inorganic framework. You take the precursor, cobalt molybdenate, you heat with nitrogen inert gas, they become COMO4 oxygen, contain a small amount of nitrogen. Then we sulfide this. Sulfidation of the book sulfide catalyst. You can get gas sulfiding H2S and liquid sulfiding. Gas sulfiding, it generates a lot of heat. Liquid sulfidings, you don't generate a lot of heat. Next. Okay, so I show you the supporter catalyst on the left hand side, and you can find that the supporter catalyst, the behavior, and compare with the supporter catalyst, the book of cobalt moly sulfide catalyst, and the red part is liquid sulfidations, and gas part is gas sulfidations. And so if you want to use book sulfide catalyst, the thing to do, we have to use liquid sulfidations instead of gas sulfidations. Okay, for the stable hindered catalyst. Okay, for stable for DBS, DBT, it's a reverse, is true. So so for both sulfide catalysts, I think generally speaking, we like to use liquid sulfide sulfidations. Yeah. So the most important difference between the supporter catalyst and both sulfide catalyst is the staggering hindrance. Staggering hindrance is a sigma absorption, and both catalysts is the pi absorption is a flat, and sigma is vertical. Then our finding is that for both sulfide catalysts, if we use liquid sulfidations, we have very low stackings, and that will increase the activity of the catalyst. So we have developed bimetallic book sulfide catalyst and not trimetallic book sulfide catalyst. So I plot the HDS activity versus HDN activity. And the right side corner bottom, the blue colors, so all book sulfate catalysts. The bottom one is the bimetallic iron moly, chromium moly, 5.9, 14.4. Then we have a trimetallic chromium iron moly. Okay. Then you have a chromium nickel moly. You get tremendous activity jump, 4.6. Okay. Chromium 0.5, tremendously. Good. The number in the parentheses is the selectivity. Okay. The activity, which means that if you want to use the book sulfate catalyst, trimetallic is preferred. Dimetallic is not prepared because the bimetallic catalyst is lower than the supporter catalyst. So the bottom line message here is the trimetallic metal sulfides is more active than bimetallic metal sulfides. This is an experiment done against LCCO, which is very fractal, very difficult to treat oil. Yeah, the difference between, you can see the difference between bulk and the supporter. The red color is a bulk and a bulk and supporter catalyst. Yeah. And the bulk sulfate catalyst is highly HDN selective. Yeah, actually, if you have a HDN selective catalyst, it's very good, useful to use hydrotreating or lubricating our oils. You can increase the viscosity index. And we found that the HDN selective catalyst, it can be used for improve the viscosity index of lubricating oils. And these are the difference between the bulk versus the supporter catalyst. The chromium's higher than iron moly and higher than the supporter catalyst. And we do a lot of characterizations. So we found that all the catalysts on a single layer are more for the phase. And we didn't see any phase separations. So let's take a trimetallic nickel molybdenum sulfide catalyst. And as I mentioned, that both sulfide catalysts have a high hydrogen powers. And this is we look at the structures. Okay. And because it's the book sulfate catalyst, we know they have a high hydrogenation index, 2.9. And the stacking height is average about 3.6. And again, this catalyst very high activity for hydrogenation, but it is much more vulnerable to nitrogen inhibitions than the supporter catalyst. And in 1990, I have done some experiments to how to combine the support and the book sulfate catalyst so they can generate some type of synergetic effects. Okay, because we know the pro and the cons of book sulfide and support sulfide catalyst, and can we generate some type of synergetic effect? So why we come up with a process called stack back reactors or catalyst stagings. Okay, so you have a two type of catalysts. Okay, we use life cycle oils, have 1.3.5% sulfur, 15 ppm of nitrogen atoms. So you will use supporter catalysts, let's say cobalt moly supported on silica alumina, and the HDS activity is 7.8, HDN is 0.73. If you use a nickel 0.5, manganese 0.5 molybdenum sulfide, book sulfide catalyst, you find that HDS is lower, HDN is higher. But HDN higher because the book sulfide catalyst have a high hydrogenation selectivity, and then favors the HDN reaction. That's why the HDN is higher. And if you have a mix the cobalt and the nickel monocatal mixer, 50-50 mixer, they found HDS of 7.7, 0.5. Okay, HDS higher, still lower than the first one, the 7.8. Okay, now you put it the nickel moly and the cobalt moly, the yellow ones on the back. Okay, the first one is the supporter catalyst. The second one is the book sulfide catalyst. The third one is put the book catalyst in the front, the supporter catalyst in the back. Now, if you the last one is you put a supporter catalyst in the back in the front, then the book sulfide catalyst in the back. And which one is the best? And find the last one is the best. Okay, if you have a 50-50, you put a supporter catalyst in the front, upstreams. Put it downstreams. The best result is much higher here. Okay, so which means that the book sulfide catalyst is not very vulnerable to nitrogen poisoning. The supporter catalyst is very, very delicate. They are very selective for hydrogenation, but they are not very strong to fight with the poisoning nitrogen compound. So the best configuration of the stack back reactor is to put a supporter catalyst in the front. You generate some activity to remove a small amount of nitrogens and then protect the book sulfide catalyst in the back. So the HDS activity is 10.5. The HDN activity 0.7, pretty higher than all the catalysts before. So the step back played the strength of supporting the book sulfide catalyst and the optimized hydrogenation and hydrogenalysis is a trade-off. Okay. So in order to do this, we have to find how to design an optimal stack back reactors. And here we can write down the mass balance reactions balancer. And you can use the different type of case, like say, delta is a supported bar, is a both sulfide catalyst. So you can want to solve the equations. Then you have a sulfur in the products. If you use a constraint optimization procedures, you can find what is the best configurations. Yeah. Then we found that the preferred stacking configuration is diagram here is this is a eta. It's the dimensions number. Is HDS activity, and here is HDN activity and selectivity, and we can plot the different four regimes. Here, if this catalyst in this yellow regimes, you still have designed a catalyst, put a support catalyst the bottom upstream downstreams and support catalyst upstreams. Here in the blue case, here's the reverse, book front and support catalyst, and also support catalyst along and the support catalyst at the bottom. So it depends on different situations. So which means you have to calculate the all the parameters here. You have to do kinetic studies here. So you suppose I'll give you one example here. If you put everything in support catalyst, okay, you put a support catalyst, a small amount of book catalyst in the bottom, and you put a total is 100% book sulfide catalyst, and we can if you look at the consumption of hydrogen, and here you can see that you put a small amount of book catalyst in the upstreams. Okay, this is downstream here. Then you have a lower low sulfur here. So this is the middle one is preferred configurations. Yeah, yeah. So basically, I think the stack bag reactors should be very promising, and the approach here is that you have to understand the mechanism. To understand the mechanism, and you have to use model compounds and use real feeds, and you can define the catalytic chemistries, and you can differentiate the hydrogenation site versus hydrogenated sites, and you have to understand the inhibition effect of organic compounds, because 5-member rings carbazole is much more dangerous than 6-member ring. Quinoline is not important. Carbazole is more important. Then we found that books-sulfate catalyst is very selective toward hydrogenations. So both, they have a pro and a cons. And the best thing to do is use stack bag reactors. You can find a synergism between the book and supporter catalyst. Okay. And basically, the last comment I had to say is that in order to prepare trimetallic metal sulfides, there are two methods. One, you can prepare in the organic mediums, the aqueous mediums, but organic mediums is very expensive. And I think if you use aqueous mediums, then the trimetallic books-sulfate catalyst should be very useful. And as a matter of fact, and this trimetallic aqueous medium catalyst, it can be commercialized. Thank you for your attention.
Thanks, Dr. Ho, for his wonderful talk. And I think, at least for me, I have a better understanding, especially for this kind of industrial process of the HDS and the HDN. So I think we are open to the question now. So if you have any question, just raise your hand. And I think here, Sonny.
Thank you, Dr. Ho. Wonderful lecture. Very important lesson for us. Just as one technical question and one more practical one. The trimetal catalyst, why does it work that much better compared with a bimetal one? Do you have an understanding?
We collaborate with Albemarle. Do you know Albemarle companies? Albemarle is a catalyst maker.
Yeah.
Company. Yeah. Albemarle company is a catalyst making company.
Oh.
Yeah.
Yeah.
And we do aqueous. We start off with organic mediums, but I think aqueous is cheaper. Yeah.
The practical question, is ExxonMobil using the stack catalyst now?
I don't have we collaborate with Albemarle. Yeah. But I think the books-sulfate has been commercialized, yes.
Okay.
But has to be aqueous.
Academic Hall, I'm Steve Yu. So now is a fellow at the Institute. So I'm very excited about your talk. Actually, my research, some of the project involved with the distal spillage in the soil. So turns out Taiwan has a law to define the sulfur content in the distal. So we changed actually the regulation getting tighter. In the 2005, the sulfur content has to be restricted to 50 ppm. And up to 2011, the sulfur content lowered down to 10 ppm. I think your research has did a lot of contribution to this kind of regulation for our environmental protection. then turns out the dibenzoyl has become a very important biomarker for determination of the spill oil. So one thing can be important is I have been always wondering, we don't really see your hydrogenolysis products in the diesel after production. So those things are also part of the diesel or not. I think that could be the crucial part for us to determine whether those compounds are still there or not. So that's probably the first question I'm asking. The second question I'm asking, because you are comparison, because catalysis, the most important thing is selectivity. So you mentioned one thing very important in terms of the nitrogen the selectivity between nitrogen heterocyclic compound and the sulfur heterocyclic compound. Those are very important. But in oil, there's naphthalene there, anthracene there. So what's happened with the selectivity? So I think during the hydrogenation process, so those compounds also being hydrogenation. So basically, the property of oil will also affect. Could you also comment about the impact in this, in the application of your catalyst? So those are the two questions I'm asking.
I think I show you a GC spectrons. We have a oil that we collect after deep HDS reactions, and we want to find the residual nitrogen compounds, and we found the predominant compounds, carbozols. So we use the carbazole as model compounds. They are the troublemakers. So I'm not sure I answer your question or not. Yeah. So.
Yeah. My question is, what's happened with the regular polyaromatic compound? For example, like naphthalene, anthracene.
No,
so
aromatic
apply...
Okay. For HDS, deep HDS reaction, hydrogenation aromatics is not an issue.
Okay. I see.
It's not an issue.
So basically, you have very high selectivity for your dibenzoyl desulfurization process. Basically, those compounds will not affect.
Yeah. Aromatic hydrogenation, this type of conditions is no thermodynamic equilibrium concentration problems. So aromatic is not an issue at all.
Okay. So they will still remain there.
Yeah. You want to remove nitrogen and sulfur to the minimum.
Okay. That's the beauty about your catalyst. That's wonderful.
Yeah.
Thank you.
Right.
You answered my question.
Very highly hydrogen powerful. Yes. Yeah.
Okay. Thank you.
Yeah.
And I think we have a question from online, right?
Yeah.
Hi. Is it okay for me to ask Dr. Ho about
Yes.
this?
Yes, go ahead.
Okay. Hi, I'm Mr. Ong from IOC, and I have a question about the vacancy created by your reaction for the sigma bond and the pi bond. So could you elaborate what it means, the vacancy for your catalyst in the molybdenum sulfur? Is it dislocation of the sulfur atom from the molybdenum matters? Thank you.
You talk about the sigma pi bonding?
Yes. It seems like your pi bonding has a lot of vacancy.
It's flat. Pi bonding is flat. Sigma bonding is vertical.
Okay. So what is vacancy in more? You could describe the vacancy of what it means the vacancy. I not quite understand for that.
Vacancy side, right?
Yeah.
I'm not sure. The metal sulfur catalyst do have you have some separate structures, okay, and you have
Okay.
multi-sulfurs, you have vacancies, yeah, right.
Okay, so
And
it's
if there's vacancy, you can the molecule can have absorptions, yes, yeah.
okay. So it's not like the maybe dislocation or the some sort of dislocation of your sulfur atom from the monoatom structure, right, or the cluster.
I think what I think that if you look at the papers by Russ Canali, SCHINELLI, Canali paper. Okay, they have some elaboration there. Basically,
Okay.
yeah. Do you know
Okay.
Russ Canali?
No, because I'm not the surface chemist, so probably I'll look up the paper. Yeah, sure. Thank you. Yeah.
Canali, yes, yeah.
Oh,
Yeah.
thank you, Dr. Ho.
Yeah.
So any other question from the audience here or any question online? So actually, Dr. Ho, I have a quick question.
Yeah.
So I just wonder when the one you use for a supported catalyst, do you think the surface acidity is going to affect those kind of the selectivity for HDS since you use the aluminum silicate, right? So I just wonder, in general, this kind of surface acidity would affect in terms of absorption of those heteroatom cycle compound or not.
Acidity unsupported for hydrogenating is non-issues. Acidity is very important for FCC. Cracking is important, yes. Yeah, acidity is important for cracking, yeah.
Okay.
For example, for hydrocracking, acidity is also important. We're not talking about hydrocracking here, yeah.
Okay. Any other question? All right. So if there's no more questions, so please join me to thank Dr. Ho for his lecture today. Again, thanks.
Thank you very much. Yeah.